come back for a second now and look at the geometry. Here's the particle moving at this instant. At this instant, it's moving straight upward. There's this applied force acting to it. So what's going to happen to the path of the particle? This is an unbalanced applied force. It's going to start coming out in the y direction, isn't it? Only in the y? It looks like the only acceleration's in the y. So, and the velocity was straight upward, had no x component going, did it? No x component or y component on the velocity. So I think it's just going to arc up this way. Now, go back to your statics background for a second. Notice that this point, the line of action of this force, is passing through the xz plane where? It's back up over here, isn't it? Isn't it back up here? Here's the line of action of that force. See it? And so look at the moment created by that force about O. Around the axis, the x-axis here, with my right hand, see it? It's negative on a lever arm of C times F, isn't it? C times F, and it's negative, going back in the negative x-axis direction, because the force is up here above. And that should be a negative C times lever arm, or times force F. And this is 90 degrees right here. It's a 90-degree angle. Something from statics, negative CFI. Right here, negative CFI. Okay, let's go back over there and observe that this line of action of this force is on this side of the YZ plane. It's out here on this side of the YZ plane, and the force is out on this side of that plane, and so the lever arm off of that YZ plane is this distance right here, which is our A. And with our right hand, F, R cross F, is upward. So we should see an AF K hat positive term. AF K hat. So the mathematics and the graphics all tie together. Okay. It's always good to spot check those if it's not too cumbersome to spot check it with another approach. In this case, the graphics lent itself nicely. Okay. Let's go ahead and, any questions on this stuff so far, conceptually, or?
The units on the rate of change in this angular momentum?
Okay, it would be the time derivative of Newton meters seconds, wouldn't it?
Yeah, so it's Newton meters?
Be Newton meters, wouldn't it? So it'd be Newton meter seconds time derivative, which would be then Newton meters, which it should be, because it's the torque.
Right.
Yeah, R cross F. Okay. Any others? Okay, good. You can do very powerful concepts involved here. I think I have time for, oh no, I'm gonna let you folks percolate a little bit with some homework on these over the weekend, and then if you have some questions we can come back at this maybe early next week. Let's go ahead and move on to impact material, impact concepts. And in the interest of time, I'm going to show you a couple things in the text, and then we will put a couple things up on the board. Okay, first of all, under impact, direct central impact. This is where two bodies, they may be heading towards one another, or, as they've illustrated right here, one may be overtaking the other. Two railroad cars in a yard. Okay, two railroad cars in a yard, one overtaking the other, and then they come together, couple together, and then roll down the track, and under the action of friction, and start to come to rest. Okay, classic example. Those little balls that you see strung on wires between supports, you pull one back or a couple of them back. That's impulse, that's impact, and that's impulse momentum kind of concept. Little pendulum type of action. So, what happens before impact? You have one body overtaking another, or two bodies approaching one another. Then, during the impact, there is an instant where, as shown here in the middle, where both bodies, even during that impact, there might be some deformation going on, and the force is pushing against each of them. One mass pushes against the other, and vice versa. And there's one instant during that impact where they happen to momentarily be moving at the same speed. Just an instant where that occurs. Then, after impact, they start to recover, and then one moves away from the other. It depends on several elements. What would you expect this mechanism, this dynamic mechanism, to depend on? The material, the type of material. In other words, its resilience, its elasticity. Might be something like a slug of lead, which would yield and not recover its shape. Or it might be something like a super ball or a steel ball. I was around when they first came out with super balls. I think I was probably in junior high school. Can you imagine junior high boys with super balls? You get in a room and throw that thing, and it would.
Somebody's going to get hit.
Yeah, it hurt. So they have a very, they're almost perfectly elastic. And if you drop one, like if I had one now and dropped it on the table, pretty rigid type of table, it would bounce back up to 90-something% of its original. How many of you play tennis? You always want fairly fresh tennis balls if you're a decent tennis player, because if you go like me out in the garage and pick up a tennis ball after it's been sitting there for a year, it's lost a whole lot of its resiliency. Okay, so there's something going on during impact that depends upon the material and its ability to recover its shape. Okay, that's one thing. What else would be necessary regarding two bodies interacting with one another like this? What else would be necessary as far as the calculations and as far as the actual dynamic effects? The relative velocities, right? Relative velocities. And then what else? Okay, we're doing direct central impact, so let's ignore the angle for a moment. We'll get to that pretty soon. What else?
Whether if they stick together any or not. If they come together, that's like storing energy in a spring, and if they never go apart, there's still energy stored there.
Okay, that's the elasticity thing, the resiliency we talked about a few minutes ago. So that's part of it. How elastic is the body? Its ability to recover its shape. That's one thing.
And if it does recover its shape or not after.
And does it recover its shape or not? That relates to its elasticity or plasticity. Okay, so that's good. And then there was the speed, the relative speed, and then also the masses. If nobody had mentioned masses, I was going to describe situation. Did you ever play football? I was a tall, skinny kid in high school playing football, and I'd be running down the field feeling really good, catch the ball, and what would happen with the guy, the defender, much bigger than me?
Bam!
He'd come much more massive, maybe not moving as fast as I was even, but come into me, and I just, you know what would happen to me with that, in that situation. So I got stomped. So the mass definitely plays a part of it. Now there's there's sort of an unpalatable practical example of this back in around the turn of the century, now around 1900, is they developed the .45 caliber pistol in the military. And the reason for that is it had a .45 caliber type slug, fairly massive slug, and it was used so that somebody came running towards you and you fired that bullet into them, the bullet would mushroom and stay in their body, and it had so much momentum that it would actually stop that person and throw them backwards. So that's sort of not a particularly nice aspect of it. But it's a very small mass, but carrying a large amount of momentum, okay, during that kind of condition. Okay, so how do you do the mathematics on this sort of thing? If we turn the page, here's the concept right up here. You're already familiar with it. And what I'm going to do is notice this looks like, without even looking at any of the discussion, what's this equation indicate about linear momentum? Conservation, because they're saying before impact here on the left equals momentum in the system after impact. Okay? Along the line of action of the motion. Along the line of action of the motion. Okay. Now, what happens during the impact? And we'll spend a little time on the board looking at this stuff. There's a couple of things going on. As the bodies first start to contact each other, there is something called a deformation period, a portion of time where the force of action is equal and opposing between the masses, and over a very short duration of time, there's an impulse. But they're opposing impulses. So there's no net impulse. No net impulse during the impact. Now, the bodies are deforming, and they've even shown that a little bit here on those spheres. Then, after a moment of time, once they've reached their maximum deformation, then they start to restore or to recover. So there's something called a restoration period that occurs. So during the recovery period, there's still an impulse occurring, but again, opposing impulses. And then once they finish that restoration period, they leave with a velocity. Each mass carries a different velocity when they leave. So if we write the equations then, M1, M2, and before impact we have V1 and V2. Along a line of action for direct central impact, and then after the impact is occurred, and then V1 is overtaking V2, and then after the impact we have this body moving with some, let's say they're not being thrown back the other direction. Let's just keep our defined positive direction for writing our equations. This is V1 prime after impact, and then this body is moving at V2 prime, as they indicated in the book, and now V2 prime is greater than V1 prime. The bodies separate, go on their way. So, since there's no net impulse in the system, then we have conservation in the x direction of linear momentum. And so the equation we saw in the book is that before impact, the system is carrying this much momentum, and that's got to be equal to the momentum in the system. Oh, and these are M1, M2s as well. Let's clean that up a little. if you knew the masses and you knew the incoming information, there's two unknowns in this equation. Okay? So there's two unknowns. So we need another piece of information, and that has to do with the ability of the masses to recover or not recover their character, their shape. And that's a measure of the elasticity. And so there is something called a coefficient of restitution. Let me go open on the other board here. Could be called a coefficient of recovery. And we give it the symbol in engineering small e, which is not the natural number. Okay. And this is called the coefficient of restitution. And what it is it's the relative velocity of separation divided by the relative velocity of approach. Relative velocity of separation divided by the relative velocity of approach. In the case of the symbolism that we've just used over here, the relative velocity of separation, this goes back to, we did a little bit of stuff in kinematics earlier on relative velocity. So if you wish to, you could actually go back and think about that a little bit. The relative velocity of separation is in this case, is it going to be the sum or differences of these things?
It's going to be a difference.
And keep in mind, you always write your equations based upon a defined vector direction. Okay? So if one of these things gets bounced back the other way, don't treat it as positive that way. Okay? Be careful. So what's the relative velocity of separation with the defined symbolism here?
Difference.
It'd be the difference of the two, wouldn't it? Okay. So the relative velocity of separation would be v2 prime minus v1 prime. Now, we can slap absolutes on that, and we'll do it in both cases. And then the relative velocity of approach over here. Again, the difference is between the two, isn't it? Okay, so v1 minus v2, or the other way around, your choice. Okay?
Just make certain they're both the same.
Excuse me?
We're just making certain, well, one's v2 minus v1, one's v1 minus v2.
This is after impact, and this is prior to impact.
Just changing signs.
Yeah.
Yeah.
And notice I slapped absolutes on them. Okay.
Changing signs because of knowledge of the magnitudes? Or
No, just, well,
Anyway.
yes, because I wrote this as the fact that this one was greater than that one. And I was just trying to get positive values shown without the absolutes there.
Okay, so it's always from the same object's point of view. It doesn't switch halfway through.
Correct, very important.
Okay.
Well, the key there, Daniel, is write him in terms of this axis. The axis in which you write this vector equation, this momentum equation. Because remember, this thing is really a vector equation, defined in this case scalar-wise, but in a defined x direction. In a defined x direction. Very important. Yeah.
Well, the way you're defining it, the coefficient of restitution would always be positive, so what would it really matter which one you pick?
Well, when you do some problems, you're going to find it's easy to make a mistake inside here, particularly when it's not direct central impact where we're just dealing with stuff moving along a straight line, one overtaking another or two things coming together and colliding along a straight line. We're going to look at oblique impact in a couple minutes. Have you ever been shooting baskets in basketball where there's several of you out there with balls and you're shooting at the same time? and one ball hits another before you get to the basket? Yeah. So that's called oblique central impact, where they're coming in at different angles to one another. Okay.